Welcome everyone to our presentation on IR spectrum ADAS obstacle detection with YOLO V7. My name is Kshama Dhadutia and I am here with my team members Abhinav Gupta and Richard Kaufman. In this project, we aim to explore the capabilities of YOLO V7 and thermal cameras in detecting obstacles in real-time low-light conditions. The YOLO V7 is a state-of-the-art extension of YOLO algorithm which is known for high accuracy and real-time performance. We are using the Teledyne FLARE ADAS dataset for training our network. This dataset includes thermal as well as RGB images of the road ahead and annotations of objects of interest such as people, bikes, cars, lights, signs, and more. The Teledyne FLARE free starter thermal dataset provides a fully annotated thermal and visible spectrum frames for development of object detection neural networks. The data was constructed to encourage the research on visible and thermal spectrum sensors for fusion algorithms in order to advance the safety of autonomous vehicles. A total of 26,442 fully annotated frames are included with 15 different object classes. A total of 9,711 thermal and 9,233 RGB training and validation images are included with a 90-10% training and validation split. The scope of this project is considering only 5 of these object classes that will be people, bikes, cars, lights, and signs. These images are captured by a thermal and a visible camera mounted on a vehicle. We can see the specs of these camera here. Here, we are looking at a comparative study of real-time object detectors' performance and the YOLO network architecture. The YOLO V7 surpasses all known object detectors in both speed and accuracy in the range of 5 frames per second to 160 frames per second and has the highest accuracy of 56.8% AP amongst all the known real-time object detectors. The YOLO models are a single-stage object detectors. In the YOLO model, image frames are featurized through a backbone. These features are combined and mixed in the neck, and then they are passed along the head of the network. YOLO predicts the locations and classes of the object around which the bounding boxes are to be drawn. The YOLO conducts a post-processing via a non-maximum suppression to arrive at its final prediction. This is how the YOLO network architecture works. Let's move on to the project overview.
So here we have an overview of what the key stages in our experimentation involved. We have the FLAIR data set, which we pass to the YOLO V7 Lite network, which is pre-trained on the COCO dataset. We split this into two different parts. The first one is training on just the RGB portion of our dataset, and we do a complete retraining of the model for 50 epochs and a batch size of 16. We do the train validation split of 80-20 and set a confidence threshold for inference of 0.25, which means that any detections below having a confidence value less than this will not show up in the inference stages. On the other side, we have training on just the thermal portion of our dataset. We split this into three parts. The first one is complete retraining, which means we don't do any transfer learning. And the rest of these two, we do some transfer learning in which we freeze the backbone of the network, which is layers 0 through 50. And in the second case, we freeze all the feature pyramids, which is layers 0 through 66. The parameters are kept pretty much the same, and except that we experiment with two different batch sizes of 16 and 32 in this case.
Once we trained a model with the thermal image data set, we wanted to evaluate how well this model would perform at detecting objects. And specifically, we wanted to see how well it would do when we applied the test data set provided by Teledyne FLAIR. So what we did was we looked at the performance metrics calculated by YOLO V7. So this is precision, recall, and then average precision at different IOU thresholds. So how these values are calculated is we take the total number of true positives, false positives, and false negatives that are counted when we run the test set through the model. Now, we use these to calculate the precision and recall values, and we ended up getting a different number of precision and recall values since we find these TPFP and FN values at different IOU thresholds and different confidence probability thresholds. So once these are found, we can also find an F1 score. And again, this F1 score is calculated at different confidence probability thresholds, which allow us to make the curve that you see on the bottom right. Now, this curve is then used to calculate a singular precision and recall value that we're going to use to evaluate how well our model's performing. So these are the P and R values found at the confidence that produces the max F1 score. We can also use these different precision and recall values to produce a PR curve, so a precision recall curve, the area under which we can find the average precision. Now, we find this average precision at a value, an IOU threshold of 0.5, and then we also average the AP value over IOU thresholds ranging from 0.5 to 0.95. So the area under this curve, the higher the area, the better the performance of the model is with regard to object detection. So here's an example of what applying our thermal model to a test set would look like. So we see we have our 4 metrics up top, and then in the first column we have our 5 object classes. And we see a pretty mixed performance. So for example, cars and people, we get average precision values over 0.8, so pretty good performance, but others like bikes, we see very weak performance, and it was hardly able to detect any bikes at all. So we discovered a lot of this had to do with how many labels were present for each object class in the test set. So people and cars, you can see, substantially have more labels than the other object classes, and this ended up leading to the trained model being better equipped to detect those objects in the test set. So you can see this behavior visualized in the PR curve on the right. So for people and cars, for example, the recall stays high at high precisions and the precision stays high at high recalls. And consequently, this has the largest, these two have the largest area under the PR curve, so the largest average precision. So we wanted to compare next the performance of models trained with thermal and RGB data. We also wanted to compare our trained models with some baseline models. So Teledyne FLIR actually trained their models to their RGB and thermal data using YOLO XM neural network. And they published the average precision they got for people and cars. So we also trained our models to the same data set using the same train validation split, and we ended up finding that our values were higher than the ones found by Teledyne FLIR. So this definitely speaks to YOLO V7 being a more accurate neural network that produces more accurate models for object detection. We also wanted to compare our model to another one that also was trained with the YOLO V7 neural network. So we found we found a model trained to the COCO data set and applied the same test images. And we found, again, that our model performed better. We can also see that at least for the models trained with the Teledyne FLIR data, that the thermal images ended up performing better consistently over the RGB image models. And with this, we can say, there are instances where training models with thermal images end up producing, more robust results for object detection. And finally, we also wanted to do a quick look into transfer learning. So in addition to training the full model, we trained other models where we froze certain portions. We froze these to the pre-trained weights, which in this case were from the model trained with the COCO data set. So in all cases, we found that when we trained the full model, we ended up getting higher average precision. Though between the two, when we froze the very end, so the last layers of the neural network, we ended up seeing higher AP values compared to when we froze the front. So if there's ever a case where transfer learning needs to be applied to save time or expedite training, then freezing the backbone of the YOLO V7 network would be preferable.
So here are some demonstrational videos from our experiments comparing the performance of the completely retrained models on RGB and IR data, respectively. We have the top rows showing the inference performance of the RGB model and the bottom row showing the inference performance for the IR models. We take 3 scenarios into consideration: a night scene, a daylight scene, and a night scene with some inclement weather in the form of rain, but is well lit. So in the first case, we can see that there is clearly not enough information in the RGB frame for the model to detect anything, specifically the human walking across in the frame. Whereas the IR model is able to pick up the human and perfectly track him moving across the street, barring some few false detections. Right. In the second case, which is a broad daylight scene, we expected the network for the RGB model, RGB data to perform well, and it does. In the second case, the IR model is fails to pick up certain things like both traffic lights at the start of the video clip. So it can be inferred that scenes with sunlight, which essentially points to stray IR radiation, will have noisy IR images based on the equipment, the camera which is picking up these images, and an RGB network will potentially work better in the case of a daylight scene. Lastly, here's a scenario with rain in the picture. The RGB model, is decidedly worse in this case, potentially due to some lens occlusion by the rain droplets on it. At the start of the video, though, we can see that the IR camera does not pick up any headlight glare, and we also know that IR radiation permeates farther in inclement weather like fog or mist, which further highlights some benefits to using this model during inclement weather conditions. So we saw in the last slide that each model, the RGB and IR models, tend to perform better under different conditions, and clearly there is a need to facilitate both of them into a single entity. Because of that, we provide a simple architecture to switch the inference based on the scene lighting conditions. So what I've done in this case is utilize both of these free-trained models and establish the time of day based on what the input RGB frame is seeing. And the assumption is that for autonomous driving conditions, the vehicle will be on the road and the top half of the scene will potentially show the skyline. And we can look at the skyline, maybe a grayscale version of the skyline to determine if it is too bright, if it is too dark, and based on that, we can switch our models. So in the first case, we can see this is still from the dataset, which shows that this is the input RGB frame, and we see the top half of the frame is pretty bright, and because of which the model just uses the pre-trained RGB model to infer the bounding boxes onto the scene. In the second case, we have the input RGB frame and the corresponding IR frame, but we see that the scene is too dark, and the architecture basically crops out this part of the image, binarizes it, and checks the average pixel values in this top half, and based on a set threshold, we switch the inference to just the IR frame. So we can see that the IR frame is actually able to see a lot more than what the input RGB frame sees. And the IR model is used to infer with the bounding boxes, is used for inference, and then this is overlaid onto the standalone, onto the RGB frame in this case. So there are a couple of problems with this in the sense that the two systems are, placed slightly apart. So there's a perspective difference, which is why remapping the bounding boxes from the thermal camera to the RGB camera might pose some challenges. But this works for most part in the center of the image. So basically, we can crop out a region of interest inside, which does not, in the center of the RGB frame, which does not extend radially outwards too much. And we'll see the bounding boxes actually being tracked across very well. So this is a slight extension to a project, but I think it's a valid addition in the sense that it fuses both of these models together and could potentially prove useful. And with this, we come to the end of the presentation. Thank you for listening.